Welcome to the course Excelling with Mathematical Modeling. Today we will be learning about some very basic models, namely the linear model, a quadratic model and a cubic model, and where you can use them. Let's go for the linear models and we start with an example. Suppose salesperson selling some product, in this case it is a detergent, it can be Surf Excel, it can be Ariel. So, they put it in a small pouches and the salesperson goes from home to home and sells them. So, let us take that the price of each pouch, say it is 30 rupees, and he has target to sell X numbers of them. So, the simple mathematical model is y, which is a function of x, where x is the number of products or number of packets that he will be selling, 30 is the price and your x is greater or equal to 0. So, obviously, if your x is 0, then there is no sale and he takes home 0 rupees, and as your x increases, his sale increases and we get a very simple model y equal to 30x. Let us take another quite simple model. Say you borrow some money from a friend and you want to repay him. So, you tell that okay, I will give you 1000 rupees or say 200 rupees every month. So, you have borrowed 1000 rupees, you want to repay him 200 rupees each month. So, I multiply it by the time, I add them, but after 1 month your 200 rupees will decrease. So, obviously, this will be minus. So, now you have a y as a function of t, which is equal to minus 200t plus 1000. So, obviously, if you put the first month t equal to 1, your y1 is minus 200 plus 1000, which is 800, and it continuously decreases every month till your balance is equal to 0, and you can see that if you solve this equation, your answer is t equal to 5 months. So, in 5 months you can repay him back. So, this is one of the simplest example of linear models. So, where you use this linear models? So, basically you will be using this linear model in such a situation where there is a constant change, whether it can be increase or whether it decreases. So, in the first example, the constant change is this 30. So, as your number of product increases, it increases by the multiple of 30, where here in the second example there is a constant decrease of 200 and hence it comes with a negative sign. So, these two are the examples where your linear functions can be used. So, let us take the example of a quadratic model. Before I go into this model, let me start by saying that we consider the case, say a particle is moving with a constant acceleration. If I want to write this in the form of the differential equation, so I know that if f is my acceleration, so df dt is some constant. So, this is dv dt because rate of change of velocity, that is some constant acceleration f. So, my next step is to integrate it f dt, and I will get v equal to ft plus some constant. If I want to find the value of constant, I need an initial condition and say at time t equal to 0, your initial velocity is u. You substitute it here and you get u equal to 0 plus constant, which gives the value of the constant to be u. So, you get your equation v equal to u plus ft. Then v is the rate of change of distance with time. So, it is dx dt, which is equal to u plus ft. If I integrate, I get x equal to ut plus half ft square plus some constant. Again, I apply the initial condition, say at t equal to 0, you have x equal to 0. So, if I substitute, I will get my constant to be equal to 0, and you get the formula. This is equal to ut plus half ft square. You are all familiar with this formula. You have learned this in physics, that v equal to u plus ft and x equal to ut plus half ft square. Suppose I change this initial condition and I write that at t equal to 0, I have x equal to x0. Then your value of the constant is going to be this, all of them going to be 0, but constant is now x0. So, you have the formula that x equal to x0 plus ut plus half ft square. Now, let us come to the problem. So, you have a person standing on a platform which is 20 meter off the ground. The person throws the ball in the air with some initial velocity 5 meter per second, and so that it lands on the ground and not on the platform. So, basically the person is standing on this platform, throws the ball and it goes down and the ground. So, this is your platform and this is your ground. So, there can be many questions. One of them is how high the ball will go and when it will, what time it reaches its maximum height. Now, if we take say v0 to be the initial velocity, so it is exactly the same formula, the formula which we derived, that gives x equal to x0 plus ut plus half ft square. Now, if I compare this x is the distance, so which is ht here, x0 is the initial condition, so it is the initial height h0, f is the acceleration, here g is the acceleration due to gravity, and since you are throwing the ball up, it is negative, so minus gt square, and u is the initial velocity, where v0 is the initial velocity. So, basically it is exactly this equation, only written in different notations. In this particular problem, we have we take our value of g, that is 10 meter per second square. The v0 is the initial velocity, so which is 5 meter per second, and the initial height, the platform, is h0, which is 20 meter. So, you put all these values here and you get it as some function of h, which is also a function of time. So, minus 10 t square plus 5t plus 20. Now, we know that it is this quadratic equation, a quadratic expression, and if we plot them, we will be getting a parabola. So, we put it in the parabolic form, of the equation. So, what we do is we just make this a whole square. So, you take 10t square minus 5t to this side, and from here you take minus ht plus 20. I take 10 common, which is t square minus 0.5t, and I take minus common, so ht minus 20. So, basically I will divide it and I make it a whole square. So, I will get t square minus 2 into a into b 0.25 this is multiplication. So that the product is 0.5 plus 0.25 square minus 0.25 square. So, I am trying to put it in the form a minus b whole square. So, this is on the left hand side, I divide it by 10. So, minus 0.1 h t minus 20. This will be t minus 0.25 square. This is minus 0.1 h t plus 2, and this 0.25 square comes to this side and gives you 0.0625. So, if you add them and put it in the form, so it will be after simplification 0.25 whole square, which is equal to minus 0.1 and h t minus 20.625. So, after simplification, this equation you put it in this form and then you have to plot. So, this is the equation. If I now plot it, I am going to get a parabola something like this. So, what is the top part? This is the top part, and if I, so approximately this is going to be 0.25. So, this is the time and this is the height h t, and the maximum height reached is this, which I can tell from here it is 20.625. So, what is your conclusion? So, in this case, this quadratic function, the vertex is a global maximum. So, every time you will reach a maximum at this point vertex, and this can be used to model this falling object. So, the conclusion is from this model that the maximum height that will be reached is 20.625, and which is 0.25 seconds after the ball is thrown to the air. And similar situation, some quantity which say decreases and then increases, means if you get something like this, you can reach a global minimum at this particular point. So, then also this quadratic function is used where you want a global maximum or a global minimum. Let us move to another interesting example. Say somebody wants to open a company, a startup company of some product, I take say aftershaves. So, you have to make an initial investment obviously for the setup, which is 7 lakh, and the cost of manufacturing each of these aftershave is rupees 110. Fine. So, what other things he need to know? So, he need to know the market. So, obviously, there will be some demand and it will follow some function, some curve. So, he does the market survey and come up with this curve. So, this is your demand curve. On the base of this, he create a function, say the demand function for the unit cell. And this function is 70,000 minus 200x, which is this line. So, with some data he got this plot and he believes that its demand will depend on this function and x is the price. So, if your x is 0, clearly you end up giving up everything free because it is only 70,000. If your x is 350, then you get your demand curve is 0, that is there is no sale basically. So, you have to find this value of x. So, that is the whole idea of this problem, that what is that x such that the startup company shows a profit and can run. For example, if I put x equal to 300 say, so then it will be your D is some 70,000 minus 200 into 300. So, which is 10,000. So, you have a demand for 10,000, but I cannot just decide this value just like that. So, I have to use some mathematical modeling to get an approximate idea. So, what is that optimal value? So, what is that value of x that I should put here so that my company can make the profit? So, this is how it will work. So, this is some function demand. So, number of units needs to be made. So, unit sale, that is x. So, total sale. So, this is the total number of units and I will sell with at a price of x, which I have to determine. So, I multiply this by x. So, this is my total selling price of all the products. Now, let us go for the cost price. The cost price, you have a setup which costs you 7 lakh. So, please note this 7 lakh has nothing to do with 70,000, okay. So, it is just another number. So, this cost price plus you have the demand, which is 70,000 minus 200x, and the cost of each unit is 110. So, you multiply it by 110, and if I simplify this, I will get 84,000,000 minus 22,000x. So, this is my cost price for all the products, this is my selling price, and my profit is the selling price minus, the selling price, which is this thing, minus the cost price. So, let me rewrite it. The profit is going to be the selling price, which is 70,000x minus 200x square, minus the cost price, which is 84,000, not 84,000, minus 22,000x. And if this is simplified, this is minus 200x square plus 92,000x minus 84,000,000. Now, suppose I want to see what is my, what happens for what value x my profit is 0. So, you just put this equal to 0 and you solve the equation 200x square minus 92,000x plus 84,000,000 equal to 0. You can just use any method. Straight away you can use the formula minus b plus minus root of b square minus 4ac divided by 2a. And if you solve this, you will be getting 230 plus minus 104, and the values are 126 and 334. So, for x equal to 126 or 334, your profit will be 0 and hence you cannot choose these values. So, what you do? You plot the graph, you plot the profit graph. So, if you plot it, you will get something like this. So, again the global maximum. So, this is your price and this is your profit. So, this is the maximum value of x you can choose at the vertex. You just drop it and you will get this value. In this case, it is 230. So, if you choose your x to be 230, then your unit cell, which is the demand graph, 70,000 minus 200 into x, which is 230 here, that is 24000. So, this is the number which will bring you the maximum profit. And then the cells, that is 24000 multiplied by x value which you have determined, which is maximum at the vertex, and this gives you 5520000. Your cost price is 7 lakh plus the number, that is 24000 multiplied by the cost price, which is 110, and this number is 3340000. So, your profit is the selling price minus the cost price and 2180000, which you can get from here also. This gives you the profit. So, the number is quite encouraging, and so one can go with this startup company for aftershaves and can make better or higher profit in the near future. So, that is another example where you use this quadratic modeling to solve the problem. Let us take another example. So, in this particular example, you have a steel sheet. So, the rectangular frame which you see is some steel sheet. I ignored the thickness of the sheet. Now, you have been asked that you have to build or to make a steel frame. So, you were told ki okay, you cut up inside, take this rectangular sheet out, which is again given that it has to be 5 by 10. Say I put centimeter. So, 50 centimeters square of the steel sheet has to be taken out with the dimension 5 by 10 or 10 by 5. And so, what is going to be this width which you take as x, such that the area of this frame is 30 centimeters square. So, that is your problem. So, again you have to calculate, say what is the area of the steel sheet before cutting. So, if this is your 10 and this is your x and this is your x, so the total length is 10 plus 2x and with the similar argument, if this is your 5 centimeter, this is x and this is x, then it is 5 plus 2x centimeter square. If I multiply, this is 50 plus 20x plus 10x plus 4x square. After simplification, it is 4x square plus 30x plus 50. Now, you have taken a sheet out which is 50 centimeter square. So, area after cutting, which is 4x square plus 30x plus 50 minus 50. So, you are left with 4x square plus 30x. So, again you have to plot this curve and get the global minimum in this case. So, if I plot it, I will get the curve like this, but this value has to be 30 centimeters square. So, this is the area and this is the x. So, this is your x and this is your area. So, I draw a line where this value is 30 and I draw a line parallel to the x axis, and it has intersected the curve at here and at here. So, basically my x value will be this and my x value will be this. So, if I solve this equation, if I solve the equation 4x square plus 30x, which is equal to 30 using the formula minus b plus minus b square minus 4ac divided by 2a, square root of that. So, my value will be x equal to minus 8.39 and 0.89. So, you can see that this value, which is approximately minus 8.39 and this is 0.89. And since these are dimensions, it cannot be negative. So, you take your x to be 0.89 and your goal is achieved. So, that is how in this particular case, though there is a global minimum, but we need this particular values to solve the problem. So, this is again another example of this quadratic modeling. Let us now move into the cubic modeling. So, in this particular case, as you can see, you have a rectangular sheet and you have to make it a box by cutting the edges where the dimension of the edge is x. So, you have to find what is that value of x for which this can be done. So, first we have to find the volume. For any cubic model, it is going to be, if there is a problem of the volume, it is the cubic model that we use it. So, if this is x and again this point is x, this value is x. So, total is length is 20 minus 2x. With the similar argument, it is 12 minus 2x the breadth. Your dimension was 20 by 12. So, this whole thing was 20, this thing was 12. So, your volume is 12 minus 2x multiplied by 20 minus 2x and the height, which is x. So, you multiply. So, if you simplify this, it is going to be say 4x cube minus 64x square plus 240x. Now, if you put x equal to 2, I can calculate that this value is going to be 256 inch cube. or cubic inch. Now, if somebody tells that no, I want the value say to be the volume of this rectangular box has to be 100. So, then you have this volume formula and you write 4x cube minus 64x square plus 240x equal to 100 and you solve this equation. If you solve this, you will get this value to be 0.4751. So, the question is how you will solve this, where you have already now done Microsoft Excel, where we have seen how to find the root of this algebraic equation. So, you can use that method to get the roots of this particular algebraic equation. So, if you do that, you will get the values to be x is 0.4751, 5 and 10.53. Now, if I substitute all these values here, I will get them. For 5 it is directly equal to 0. For the other two values, up to 2 places of decimal, the values are 0. So, approximately you can choose any one of the value for x, for which your volume will be 100, and as per convenience of the shape of the box or what kind of product you are sending in that particular box, you choose your x values, but it will give you the same constant volume 100. So, this is an example where you can use the cubic model, and when we involve the volumes, we use this cubic models. So, in this particular lecture, you get an idea how a very simple kind of problem can be tackled by using this linear model, this quadratic model and the cubic model. We will take up another part of the equation where we will be using the growth models in our next lecture. Till then, bye bye.